Hello and welcome to lesson 7 of our study of optimization 1. In this lesson, we will talk about constrained multivariable optimization with inequality constraints. Note that in our previous video, that's lesson 6, we talked about constrained multivariable optimization with equality constraints. But here, we are dealing with inequality constraints. Okay, so let's consider the problem below. Now we are supposed to optimize z equals f of x subject to ji of x equals h of x minus bi less than or equal to 0. So this is the inequality sign here. And we have I running from 1, 2 to m. So that means we can have a lot of the constraints. And our x here is x1, x2 to xn transpose. Okay. So that means a multivariable function. So when we have a problem of this form, what we do is that we try to convert the inequality constraint to the equality constraint because we know the methods that we can use to solve it when we have equality constraints. So we try to do that conversion. So what we do is that we add a non-negative slack variable xi to the constraint gi of x. So take notice of this. Our slack is always non-negative. Okay. So we add it to our constraint gi of x to be able to convert it to the equality form. So if we do that, then our constraint becomes gi of x plus si squared. Okay. So you could see that now the original problem becomes optimized. We have the same objective function, but now our constraint we have plus si squared attached to it. Okay, all right. So the reason why we use xi squared is because we want our slack to be non-negative. And another reason why we do that is because we don't want to set another constraint, for instance, to say that our si should be greater than or equal to 0. So if you have si squared, then it covers this. Okay, so after we've gotten this, then what we do is that we solve this using the Lagrange multipliers. So the Lagrange function is given by L of x s lambda equals f of x minus summation from I starting from 1 to m lambda I then times whatever we have here, where the lambdas, the collection of our lambdas, is called the vector of Lagrange multipliers. Okay, so a quick recap of what we've done so far. So in this video, we are trying to solve multivariable functions when you're optimizing them and you have inequality constraints. Okay, so when you have inequality constraints, we don't have methods for solving them, but we have methods for solving them when we have equality constraints. So we try to convert the inequality constraint to an equality constraint by adding what we call a slack variable. And when we add that to our constraint, our original question, which was this objective function plus this constraint, becomes this objective function plus this constraint. Okay, then after we are done with that, then we use the Lagrange multipliers, which we already learned in our previous video to solve them. So let's go through necessary conditions. So the necessary conditions for an extreme point to be an optimal point can be obtained by solving the following equations. So we find the partial derivative of L with respect to our x's, and that should give us 0. Then we find the partial derivatives of L with respect to our lambdas, and now always give us something of this form. And we find the partial derivative of L with respect to our s's, our slack variables, and that also gives us something like this. So after we are done, we are going to get sets of linear equations. Then we solve them simultaneously using the best approaches to obtain a solution. So from equation 4, okay, so from equation 3, so let's call this equation 1, equation 2, equation 3. Okay, so other times from equation 3, we do some kind of analysis, because in mathematics, when you have AB equals 0, it's either A is 0 or B is 0, but not both. So here, since we have minus 2xi lambda I equals 0, we say it's either our si is 0 or our lambda I is 0. And because our Lagrange multiplier lambda I is unrestricted, we can vary it. Okay, so when we solve examples, you'll see what we are talking about. So we'll be taking 2 examples. Let's take the first one. So the first one says we should maximize, and we have this objective function subject to these 2 constraints. There is not a constraint, okay? It's just telling us our x1, x2s are non-negative. So this is our objective function, and these are our constraints. There are 2 of them, okay? So since we have inequality constraints, you could see we have less than or equal to. We introduce what we call a slack variable, si squared, into our constraints. So when we do that, we are now going to have the first constraint to be s1 plus s2 plus si squared minus 14. Minus 14 because we bring this one inside. Then this is the slack variable. Then the second one will give us minus s1 plus s2 plus the second slack variable, s2 squared minus 6. Okay, so now introducing the slack variables and converting our inequality constraints to equality constraints, we are going to have these. So after doing that, the Lagrange function is given by this here. So since we have 2 constraints, we are going to have 2 multipliers and 2 slack variables. So making substitution is going to give us this, because there's our z, our g1 of x, x1, and our g2 of x, x2. Okay, so after having this Lagrange function, then we take the necessary conditions. So you can see that we have how many variables here? x1, x2, lambda 1, lambda 2, s1, and what? s2. So we are going to differentiate L partially with respect to all these. And the necessary condition is that they should all give us 0. So the partial derivative of L with respect to x1 should be 0. And that should be the same as that with respect to s2. That should also be 0. This should also be 0, 0, 0, and 0. Okay. So now let's find the partial derivatives. So when you find a partial derivative of L with respect to S1, you're going to get 10 minus 2x1 minus lambda 1 plus lambda 2. Okay, so if you should find with respect to x2, you're going to get, you can pause the video and do that. You're going to get 10 minus 2x2 minus lambda 1 minus lambda 2 equals 0. And that's equation 2. Finding that with respect to lambda 1 will give you, so you come here, when you differentiate, you get negative x1. So you get negative into bracket x1 plus s2 plus s1 squared minus 14. When you take the negative out and you multiply it, you're going to get this thing here. And when you differentiate partially with respect to lambda 2, you're going to get this. Differentiating partially with respect to s1, you're going to get that. And with respect to s2, you're going to get this. So now you're going to have 6 equations. And you're supposed to solve these equations simultaneously to obtain the values for our s's, x's, and what lambdas. So what we do is that we are solving the system of linear equations. Okay, so we solve them using the best approach. So from equation 5, we have this, or we can say that here. And having this, it is either s1 is 0 or lambda 1 is 0. But we are choosing lambda 1 to be 0. So that means s1 will be a different, will be a non-zero number. We are supposed to find for that. Then in 6, we have this. We now want to is either lambda 2 is 0 or s2 is what? 0. But we are choosing lambda 2 to be 0. That means s2 is going to be a non-zero number which we are supposed to find. So that means making this, we already know what our lambda 1 is. It is 0. Our lambda 2 is also 0. So we've been able to find for 2 of the 6 unknowns. So we will use these 2 to further find for the rest. Okay. So now our lambda 1 is 0. Our lambda 2 is also 0. So putting that into equation 1. Here's our equation 1. And here's our equation 2. So that will give us 10 minus 2x1. The lambda part goes to 0 because we have lambda 1, lambda 2 being 0 equals 0. That will give us 10 will be equal to 2x1. x1 will be equal to 5. So now we know what x1 is. Then putting lambda 1 equals lambda 2 equals 0 into equation 2. So recall that this is equation 2. So that means this part goes away. So we will have 10 minus 2x2 equals 0. And solving that will give us s2 to be 5. So now putting x1 and x2 equals 5 into equation 3. Know that x1 is 5, x2 is also 5. That's why I wrote it this way. So know that this is equation 3 and this is equation 4. We're going to make substitution into them. So when we substitute into equation 3, we are going to get minus 5 minus 5 minus s2 squared plus 14 equals 0. So solving this is going to give us s2 squared will be equal to 4. So putting x1 equals x2 equals 5 into equation 4, we're also going to get s2 squared equals 6 when you solve that. Okay, so after we are done, we make a conclusion. None of our assumptions was violated. We said that our slack variables are non-negative. Okay, so since our s1 squared and our s2 squared are all greater than 0, so they are all non-negative, so they are all greater than or equal to 0, then we have a feasible solution. So the point x1 x2 equals 5 5 is the maximum point. And when we put 5 5 into our objective function, this is our objective function, if we should put x1 to be 5 and x2 to be 5 inside, we are going to get 50. So we made a conclusion that the maximum value is 50 and it occurs at the point 5 5 because the question told us to maximize. Okay, so that's the solution to the first one, which is very simple. So we'll be solving the second one, which will expose us to a whole lot of things. And I love this question a lot. So it says optimize z equals 10x1 minus s1 squared plus 10x2 minus s2 squared. Subject to these constraints. Okay, so we have inequality constraints here. So if you could recall, everything we are doing, the constraint is always of the form less than or equal to. But this is the case we have greater than or equal to. So what we do is that before we can solve this problem, we would want to change this greater than or equal to less than or equal to. Okay, so we want to change this to contain this inequality instead of the greater than or equal to. So we have x1 minus s2 greater than or equal to 6. If we decide to bring the 6 here, we get negative 6 less than or equal to x2 minus x1, which can give us minus x1 plus s2 less than or equal to minus 6. Or when you have your x1 minus x2 greater than or equal to 6, to change this to less than or equal to, you multiply through by negative and negative here, and the sign also changes. So you will have negative x1 plus x2 less than or equal to negative 6. So the same as this. So that means we've been able to turn this into that. So we are going to use this instead of this. Okay. So that means now our new constraint will be s1 plus s2 less than or equal to 9 and negative x1 plus x2 less than or equal to negative 6. So that means now we can solve our problem because we have the inequalities all being in that form. So we then try to change our inequality constraint to an equality constraint by introducing a slack. And our slack is always a non-negative variable. So introducing a slack is going to give us this to be our first constraint. It needs to be our second constraint. So the Lagrange function is formed by this here. So making substitution is going to give us this to be a Lagrange function. Okay, then we have necessary conditions. So the necessary conditions are that del x1 should be 0. That gives us equation 1. Del x2 should be 0. So when you find the partial derivative of L with respect to x1, you get this. Then you equate it to 0. That's the necessary conditions. So with respect to x2, you get this. We call it equation 2. With respect to lambda 1, we get this. We call it equation 3. With respect to lambda 2, this equation 4. With respect to s1, this equation 5. With respect to s2, we have this and we call it equation 6. So we are going to have 6 equations. So we are now to solve them for the unknowns. Okay, so from equation 5 and equation 6, so now this is equation 5, this is equation 6. We are saying if AB is equal to 0, either A is 0 or B is 0. So yes, we are saying that in this case, we want our lambda 1 to be 0 and our lambda 2 to be what? 0. So from equation 5 and equation 6, we will have lambda 1 and lambda 2 to be 0. So putting that into equation 1, this is equation 1. So we put that into equation 1. After that, we put that into equation 2. So that putting that into equation 1 will give us 10 minus 2x1 equals 0. And we get x1 to be 5. Putting that in equation 2 also give us 10 minus 2x2 equals 0. And we get x2 to be 5. So now, putting x1 equals s2 equals 5 into equation 3 and 4. So into equation 3, we are going to get negative 5 minus s1 squared plus 9 equals 0. And making our commutation is going to give us s1 squared equals negative 1. And when we put that into equation 4, so we are going to get s2 squared equals 6. Okay, but you know, s1 squared being equals negative 1 means s1 will be equal to plus or minus root of negative 1. This is going to give us a complex number because we have I squared to be negative 1. So that means I will be equal to plus or minus root of negative 1. So what this thing means is that there is a violation here. Because we're supposed to have a positive number here. So because of that, we say that the solution we had, we had s1 and s2 to be 5, 5. We say that it is infeasible, right? Our solution is infeasible. So we take a different combination of our lambdas and s1s and s2 to get a feasible solution. So now from equation 5, which was minus 2 lambda 1 s1 equals 0, equation 6, which was minus 2 lambda 2 s2 equals 0, we let s1 be 0 in equation 5 and lambda 2 be 0 in equation 6. So putting that into equation 1 will give us 10 minus x1 minus lambda 1 equals 0. And making S1 a subject gives us this. So putting that into equation 2 will also give us 10 minus lambda 1 equals 2x2. And x2 is given by this. So putting x1 and x2 into equation 3. So this is equation 3. So wherever we find x1, we put this there, x2, we put this there. And solving this is going to give us lambda 1 to be 1. Alright, so recall that this is our x. So when you make substitution, you are going to get 4.5. And this was our x2. If you make substitution, you are going to get 4.5 again. So we put this into 4 to find for our x2. And this is equation 4. So now our x1 is minus 9 over 2. x2 is minus, is also 9 over 2. So equation 4. Let's take equation 4 from what we had. So this is equation 4. x1 minus x2 minus s2 squared minus 6 equals 0. Okay, so we're going to get 9 over 2 minus 9 over 2 minus s2 squared minus 6 equals 0. And 9 minus 2, 9 minus 2 gives us 0. So we'll have negative 6. This negative 6 minus s2 squared equals 0. And you have s2 squared will be equal to negative 6. Right, so since our s2 squared is equal to negative 6, it means the solution we had is infeasible because there is a violation here. No, s2 squared should be greater than 0. s1 squared should be greater than or equal to 0. Yes. So now we move on to the third combination we can have. So from equation 5, that's minus 2 lambda 1 x1 equals 0. Equation 6, minus 2 lambda 1 lambda 2 x2 equals 0. We want to make lambda 1 0 in 5 and s2 0 in 6. So doing that, when we put lambda 1 equals 0 into equation 1 and equation 2, in equation 1 we'll get this. In equation 2, you will get this. So now putting x1 equals 10 plus lambda 2 over 2 and x2 equals 10 minus lambda 2 over 2 into equation 3, into equation 4. Or let's look at that equation number. So into, yes, equation 4. This is equation 4. So putting us into equation 4 is going to give us, so this is equation 4. So this is that, this is that. So if you should put that in, you're going to get lambda 2 to be 6. That means from there we can compute the values for x1 and x2. So we had x1 to be 8, x2 to be 2. So putting x1 equals 8 and x2 equals 2 into equation 3 and equation 3, So let's put that into equation 3. So you are going to get minus x1 minus x2 minus s1 squared plus 9 equals 0. And now x minus x1 be minus 10 minus 8 minus 2 minus s1 squared plus 9 equals 0. This will give us minus 10 minus s1 squared plus 9 equals 0. And this will give us s1 squared equals negative 1. So you can see there is a violation here as well. So that means our solution for this will also be infeasible. So now we try the last possible combination we can get, right? Then, so we are saying that from equation 5, that's in equation 6, we are letting s1 to be 0 from 5 and s2 to be 0 from 6. So when we do that, so putting s1 equals 0 and s2 equals into equation 3 and s2 equals 0 into equation 4. So this is equation 3. When x1 squared is 0, because when s1 is 0, s1 squared is 0. So we get this equation A. And putting that into equation 4, when s2 is 0, s2 squared is 0. So we get this equation B. So you can see that we have two system of equations and with two unknowns. So that means we can solve equation A and equation B simultaneously for x1 and x2. And when we do that, we will get x1 to be 7.5 and x2 to be 1.5. So putting x1 equals 7.5 into equation 1 will give us this. So wherever you find x1, you put 7.5 there, which is the same as 15 over 2. So to let us get this equation, we are calling equation C. And putting x2 equals 1.5 into equation 2. So wherever you find x2, you put 3 over 2 there, which is the same as 1.5. Will give us lambda 1 plus lambda 2 equals 7, which we are calling equation D. So we can solve equation C and equation D simultaneously for values for lambda 1 and lambda 2. So doing that, when you solve, you are going to get lambda 1 to be 6, lambda 1 to be 1, lambda 2 to be 6. And our slacks were S1 was 0 and X2 was 0, because that was what we chose at the start. So since our slacks are all non-negative, then we can what? Proceed. That means that the solution we are having is feasible. So putting x1, x2 equals 7.5, 1.5 into the objective function, we are going to compute the functional value of C. So that means we'll get 10 times 7.5 minus 1.5 squared plus 10 times 7.5 minus 1.5 squared. And if I did the computation right, I'm supposed to get 633. 633. So let me redo the computation and see if it's correct. So that's incorrect. It should be 145.5. So if you do the computation, that's what you're supposed to get. So then this means that the optimal value for this objective function is 145.5, and it occurs at the point 7.5, 1.5. Okay, so the question asks us to optimize. So that means the value we had is the optimal value, because we don't know whether it is the maximum or it is the minimum. So now we have to find out whether we are maximizing or minimizing. And we can only do this by finding out the convexity of Z. To know that this is Z, right? So we are coming to find the convexity of this. So since we have x1 and x2, we are going to use this Haitian matrix here. So we find our partial derivatives. So our partial derivative with respect to x1 will give us, with respect to x2, when you find the second derivative with respect to x1, or with respect to x2, when you find the partial derivative, like del squared f del x1 del s2 will get 0. Here, so when you find del squared f del x2 del s1, we are going to get 0 as well. So putting that is going to give us this Haitian matrix here. So finding the eigenvalues of each is going to give us -2, -2. So since all our eigenvalues are negative, it implies that our Haitian matrix is negative definite. Hence, Z, our function, is a concave function. So since a concave function, that means we have something like this. So that means we are maximizing. Okay, so the final conclusion is that the maximum value of Z is 145.5, and it occurs at the point 7.5 and 1.5. So that's how we do this. One of the times we've been calling this process the Kuhn-Tucker process. Okay, the Kuhn-Tucker. So thank you very much for watching this video. Don't forget to hit the like button and subscribe if you haven't for more content. So thank you very much, and see you in the next video.